bivalves were amongst the most important carbonate producers of the carbonate platforms of the Americas during the late Cretaceous. They developed a strange set of morphologies and feeding strategies that will be briefly reviewed. Following the major extinction event at the end of the Cenomanian, the first Rudists appeared in the Santonian and early Campanian, but are relatively poorly known. This talk will examine the feeding strategies of some of the Rudists and then look at the development of the hypertid Rudists in the Santonian. Just for those of you, Santonian 86.3 to 83.6 mega annum, and the early Campanian, the Campanian period, 83.6 to 72.1 mega annum. And so we're focusing on Jamaica. Jamaica, along with Puerto Rico, has the best developments of Rudists at this time period, and there are 5 different locations which have yielded faunas that show a progressive evolution, including a new locality in central Jamaica. A problem of dating the Rudists of this time remains in the lack of an international definition of the Santonian Campanian boundary, and some assemblages will be assigned to either the Santonian or to the Campanian once agreement is reached on the boundary. Rudists can also be used to date the limestones in which they occur and are useful in Jamaica and Puerto Rico and possibly Cuba. So this afternoon's talk promises to be interesting because it looks at some aspects of debate and of course faunal diversity among the Rudists. And our presenter is our own colleague of the Department of Geography and Geology, Professor Simon Mitchell. Simon received a first-class honors degree in geology from the University of Hull in 1989 and a PhD in geology from the University of Liverpool in 1993. He arrived in Mona in January 1996, and by 2000 he was promoted to senior lecturer, and in 2006 he assumed the chair of Professor of Sedimentary Geology. He has research interests in the Mesozoic and Cenozoic sedimentology and paleontology, the stratigraphy and geology of Jamaica, and the development of geological resources, as well as the geological evolution of the Caribbean region. And I think today's talk will fit somewhere in that juncture of the geological evolution of the Caribbean region. He has received the Moore Medal which is a Bachelor of Science award for mapping from Racy in Scotland from the Yorkshire Geological Society 1989, the Gleaner Newspaper Honor Award for Science and Technology in 2011, the Chubb Award for Excellence in Geography from the Geological Society of Jamaica in 2013, and the Vice Chancellor's Award for Excellence in Research in 2014. He's extensively published with over 140 peer-reviewed papers, spanning fossil bivalves in Jamaica, Mexico, Trinidad, Puerto Rico, the US. And he's also given back in terms of serving as the editor of the Caribbean Journal of Earth Sciences and the editor of UWI Contributions to Geology. He also serves as the English language editor for Carnet de Géologie, a French geological journal. So he gives public service in the field of geology by being a member of the Standing Committee for the Caribbean Geological Conferences. And he also serves as chairman of the Commission on Jamaican Lithostratigraphy. And he's also a member of the Geological Society of Jamaica. And of course, he serves as external examiner for a number of colleges. So we're very pleased to hear from Simon this afternoon on the work he's been doing and the insights that it will show us about Central Jamaica and its significance. Simon, over to you.
Okay, thank you very much, Thera. Yes, when I came to Jamaica, one of the things that sort of started fascinating me, well, actually, I was working on Cretaceous before I came here, and I looked at the Cretaceous here, and I tried to find out what were the most useful fossils in it. and it turned out that either it was the forams or it was rudists. And since the forams weren't that common, it turned out that the rudists are probably the most interesting ones. And that sort of took me on a voyage of understanding the rudists of not just the Caribbean, but the Americas. And certainly a voyage in terms of flying, it certainly turned out to be, because I've examined outcrops and museum collections across the region and also outside the region where they've actually been moved to, which has included places like Puerto Rico, Cuba, Mexico City, California, Austin, Texas, where there's a nice collection there, the American Museum of Natural History in New York, the Smithsonian in Washington, the Natural History Museum in London, and Naturalis in Leiden in the Netherlands. So really the material is widely distributed, and I photographed pretty much all of this material now. And you will see some of this material and some of the spectacular material which actually we come across. So what I'm going to do is dive in. There's a very large number of slides, and I tend to do that, but most of them are nice pictures of rudists. You might get fed up of rudists by the end of this, but I hope you won't, because they are quite bizarre and they are really quite interesting. Okay, so brief outline. Well, I'm going to say a little bit about what rudists are, what rudist bivalves are. Not much, but a little bit. Why are they useful? Why do we want to look at them? And then some of the questions of like, how did they feed? And this is some of the work we've recently published. We published it last year, in fact. And then I'm going to go on to some of the sites in central Jamaica and elsewhere in Jamaica that yield these Santonian Campanian rudists and the problem with the Santonian Campanian boundary, and then talk about the rudists in some more details, just concentrating on these groups and show you how useful they are. So rudists really started off in the Jurassic. They were really rather small, unassuming things in the Jurassic, late Jurassic, so about 160 million years ago. And what they did was they took over the carbonate platforms. So they took over all the carbonate environments in the Tethyan region, so the equatorial regions of the planet at that time. And they developed into all these sort of strange examples here, and I've sort of shown some of these, as I think is Peter Skelton's actual diagram. And so they grew in, they formed ones which grew upwards, they formed ones which lay sort of prostrate on the seafloor with equal valves, and they had other forms that clung to substrates and things like this. So they really tried to take over as many niches as possible in these carbonate platforms. And they were pretty successful because there are vast numbers of these things as we look across the equatorial regions. So if we think about the Americas, and it's obviously centered in the Americas, they range from northern South America through the islands of the Caribbean, so Trinidad, Puerto Rico, Hispaniola, Cuba, Jamaica, and up through Mexico and up into southern North America. So particularly Texas is a particularly important area for these sorts of things. But at different times, they spread north and south at different times. And by the time where we're talking about the Santonian Campanian, the ones I'm talking about really are restricted to the central Caribbean region. So the Greater Antilles and extending off into Mexico. A few of them did get up into California. So quick thing, what are they? Well, they come in a wide range of shapes and forms. They have two valves because they're bivalves, and bivalves have two valves, a left and a right valve. In some of them, they're more or less equal in size. In others, you have one larger valve and a sort of a little cap on the top of it. And it's the ones with these larger valves and caps, which I'll talk about at the end of the talk. Most bivalves, when you see them on the beach, you see the two shells held together by a ligament. And the Rudists get rid of the ligaments by a number of ways. It gets reduced, it gets enfolded, and in many forms, it just disappears. So it changes how they actually use their shells. Typically, there's 2 teeth, but some forms have more than that. And there are big muscles, and the muscles develop on platforms that allow the Rudists to actually open their valves and close the valves, although they probably didn't do much of that. They probably only gaped, opened their valves a very, very little bit. And they have inner and outer shell layers. So the outer shell layer is calcite, and the inner shell layer is aragonite. So typically the outer shell layer is well preserved, and the inner shell layer is often poorly preserved. But that doesn't always work like that. And sometimes either layer can be thick or thin. And in many forms, these layers become cellular to some degree, or in some cases, completely cellular. And we'll see some of this as we go through. Well, why study them? Well, one, they're an extinct and very fascinating group. So there's an interest in that way, and you can just see some of the shapes that are actually there. They actually are related to the changing climate of the Cretaceous. And so in some ways, they help us understand these ancient patterns of climate. And in many ways, that's important for us today as we are changing the climate of the world. They are also quite useful in dating our limestones. And that is probably one of the most important things. And the real problem being with these limestones is that they don't contain many things that you classically use to date limestones. The things that we commonly use, like planktic forams and nanofossils, often do not occur in these hard limestones, or you can't get them out. And so we need other types of fossil to help us identify these. And the Rudists really help us with this sort of thing. So I thought I'd start off by looking at one of the classic ones. This is Titanocyclitis, and you can see the scale bar there. It tells you something about it. It's not small. And that's quite common about Rudists. Rudists were not necessarily small things. So this one is pretty large. And this means that anybody who wants to come collecting Rudists has to be able to carry lots of material, because you can imagine that is not a light object. Now it's completely made of stone. But this is a bizarre creature. And one of the big questions is, how did this thing feed? Okay, it's got 2 valves. The 2 valves are held together at the top. You can see the junction there, the commissure we call it. And that lay flat on the seafloor. So if it lay flat on the seafloor, how did it feed? And so really, we did a little bit of a study on this and tried to put together a series of pieces of evidence that actually allowed us to work this out. So first of all, we got a very nice specimen, and this is from Malden School out in St. James in Jamaica, and we cut it up across different parts of the same valve. So you saw that big curved valve. This is a series of cuts across it. And you can see that there are a series of tubes that run through the actual shell. And it goes from the top left to the bottom right, getting progressively from the tip of the shell to the actual commissure. And you can see that there are clusters of tubes, and all those tubes develop from a single tube in the smallest example, the narrowest one. And they gradually increase in numbers until they're large numbers at the commissure. So the real question is, what was the function of these tubes? And some people have suggested they were for photosynthetic organisms. Some people have suggested that they were for ballast, to keep the Rudists, because they were relatively light things on the seafloor, whereas other people have suggested they might be conduits for fluid flow within the actual Rudist itself. And so what we wanted to do was actually have a look at this and examine this. So the first thing is, if you look at the tips of these Rudists, and this is the actual type specimen of Titanocyclitis on the left, number A, which is of course from Jamaica, from Logie Green in Jamaica. And each one of those tubes opens out at the tip of the valve, which means they were open to seawater. And they don't contain any form of septum in there, so they are continuous tubes that extend from seawater to the commissure, which does make some suggestion that perhaps water went through. Now on the right, whether you can see it or not, but there are some things in there labeled as E's, little E's, and those are little organisms, and this is a different species, but these are little organisms that lived on the insides of the tubes. And the only way you could live on the insides of the tubes is if you had water passing through the tubes and they could filter feed this water. So these must have been conduits for fluid flow from the tip of the Rudist to the commissure, or the other way around. Has to be one of the others. Now this is where the paper is at the bottom, and if anybody would like a copy, just go on to ResearchGate and text me, send me any ResearchGate thing, and I'll do it there. My grad student Gavin Gunter and my colleague from chemistry, Willem Mulder, and Willem modeled the movement of water through a tube network like this, and it turns out that sucking, in other words drawing water from the tip into the actual commissure area, is much more efficient than blowing water out of the other way. And so what we can now see is that these strange Rudists, and that's one with big flanges, and I'll explain a little bit about that, suck in water through the tip of the valve, they draw it through this tube network, and they filter feed it at the commissure, and then they must expel it out through the commissure itself. And there's this thing called the posterior ventral groove, which lies where we have some siphons in other types of bivalve. And it seems that this is basically the exhaust mechanism for getting rid of the water. And then these strange flanges, which grow up from the actual animal or are developed from the animal, are how it directs where that water goes. So in other words, if you throw it out through this posterior ventral groove, it can't come back in again. If you've already taken the nutrients out of it, you don't want it to come back again. And look where the actual tubes are. The tubes are on the other side, around the other side of the actual shell. And so we can sort of understand that these Rudists develop these really rather bizarre methods of feeding. And if you want to read the paper, there are more comments in there about this sort of thing. What I want to move on now to is the Hippuratidae. And this is another group of Rudists, and this is what the real focus of the talk is on today. Now, this is an example here from France, in fact, and it shows the typical sort of form of the Hippurites, if you like that, or this sort of thing. And so they have a large conical lower valve, a right valve, and an operculiform left valve, and you can see it there. And what they do is they have a delicate network of mesh on top of it, and again, it's a filter feeding thing. So they are filter feeding water, it's coming in through these, it's being drawn down towards the commissure, and it's being filter fed there. The nutrients are being extracted from it, and then it's being injected again. Now, when you get to the Americas, you don't have many of these. These sorts of things aren't very common, or at least these simple ones aren't. What we get is these very, very impressive, very complex ones. Now, Norman Soule, when he looked at his gastropods in basically the last century, so in the 1980s, so 1970s through to the 1980s, he looked for places where his gastropods were silicified. Okay, and what does that mean? Well, you can drop the bit of limestone in acid and all the limestone will disappear and you end up with a very nice preserved shell. And he collected this one site in Puerto Rico, which contains vast numbers of Rudists. And so sitting tucked away in the Smithsonian was this collection of Rudists. And so myself and Peter Skelton were invited there to go through a series of collections. And at that time, we photographed this material, and I described that last year. And I'm just going to show you some pictures of these. I don't expect you to read this. It's not important, but this is what they start looking like. So this is the lower valve of one of them. And I'm just going to go through these and show you some of the details. This is the top valve, and you can see this beautiful sieve plate and the top left developed in there. And so they would filter feed. So water would be sucked in through here. It would go along those little furrows to the edge of the shell, and there the cirri would actually take out the nutrients in there, the filter feed out the materials. And you can see how beautiful some of this material is really well preserved. You can't get these three-dimensional specimens elsewhere, anywhere in the Caribbean. And you see again there, you've got these really rather delicate, wonderfully preserved things. They can't move them from where they're actually stored because they're too delicate to move. If they move them, they'll damage them. So they're actually going to sit there forevermore in the storage area, but they've been given their own little set of drawers. So, and there's a whole set of these. There's three different types of these. And these ones you see, the first one just had 3 folds. These have these multiple folds coming in. And the multiple fold type Rudists are the ones I'm going to talk about as we go further forward. And again, I'll just show you the exquisite nature of the preservation of these actual fossils. Okay, and you can see again the sieve plates on top through which they would actually draw water in. And then you get into a much larger one, and this is first described from Cuba. And this is the lower shell again, and then you get pieces of the upper shell, and that's the total upper shell. And you can see the complexity of it. You see all of these basically pore systems that are in there for different reasons to allow the filter feeding to actually happen. I'm not going to worry about what the names of these things are, and just show you some more pictures and finish on the picture there of the filter feeding sieve plates on the top of this, and you can see how very, very intricate and delicate these sorts of things are. Now, I'll point out that a lot of the time we don't see this. It's very, very rare that we actually get this sort of level of detail preserved in these. Very commonly, it's just destroyed. It's not been fossilized. And it's only when we get exceptional material like this that you can actually work it out. Just to show you that the gastropods are exposed. If you look down on the bottom right, there's actually one of the gastropods there, actually preserved. So this brings me to the Santonian Campanian problem. Okay, and there are 6 stages in the Upper Cretaceous. And pretty much all the stages have been basically sorted out globally with the exception of the Santonian Campanian boundary. And one of the reasons for that is that the classical things we use for it, like Ammonites and Inoceramids, don't work. They're either not well preserved at that point, or they're very endemic. They're not globally distributed. The same things aren't found everywhere. And this has come up with a problem of how are we going to define this boundary? And the sort of classical way of trying to define this boundary is to make it somewhere about the level of the extinction of a crinoid marsupites. I will show you some pictures of these in a minute, which is broadly equivalent to a belemnite appearing in Europe, Northern Europe, and on the Russian platform, a thing called Gonioteuthis granulata quadrata. Well, that doesn't occur everywhere, and marsupites doesn't necessarily occur everywhere. So some other things have been suggested. So the appearance, I mean, nanofossil workers have generally used the appearance of this thing called Bruysonia parker as the base of the boundary, and planktic foram workers often have used the extinction of Dicarinella asymmetrica as the boundary. And there's another possibility, which is Paleomagnetic Reversal. Okay, so we all probably know that the Earth's magnetic field every so often switches. Well, through a lot of the Cretaceous, it didn't do that, actually. It was actually all pointing one direction. But as you get up towards the Santonian, you start seeing the switches coming in again. And there is one about the same level as those last 2 I talked about, which could possibly be the indicator. Okay, so I'll just show you what some of those things look like, just so that the names have some meaning, or at least you can see it. This is from my work, which I did in Yorkshire for my PhD when I was in Liverpool. Yeah, problem of Lancashire, Yorkshire transitions. But And the one in the middle is this Marsupites thing, okay? And the extinction of that was sort of the classical sort of thing that was used in the 19th century to sort of pick the top of the Santonian, this sort of thing. There's actually a series of these crinoids that occur. The oldest ones are on the left and the youngest one is on the right. But they're not globally distributed. They tend to do like chalks, and you can see these are in chalks. However, they also do occur in Jamaica, and we do not have chalks at this time in Jamaica. And in fact, Eventual socialis is really rather common in St. Anne in the rocks of the Santonian. It's actually really very, very common. You can collect hundreds of individual plates of it very, very easily. So it may not be that they're just restricted to chalks. It might be that people haven't looked for them in places other than chalks. But people don't like extinction events as boundary markers anyway. So there's a sort of growing sort of thing that we don't want to use that. This is the belemnite. In fact, in Yorkshire, it comes in a bit older than this. I sort of published that last year as well. So the belemnite, and it's only found in Europe, so it's not going to be a good marker for this sort of thing. And then you've got the nanofossil on the left. Look at the size of that. It's 2 microns, that scale bar. So this is a very small thing. And then the planktic foram on the right. These probably will work in Jamaica. We will probably use those in Jamaica. So they would quite reasonably work. But there's maybe a couple of million years difference between the extinction of Marsupites and the levels where this sort of happens. So it actually does make a difference on what you call something. And so that's why I called it the Santonian Campanian problem at the present time. Right, so let's go back to our Rudist friends. Now, the classic other type of Rudist, other than Titanocyclitis, is Barrettia. And this is this Hippurotid, which doesn't just have 3 folds into the shell, but as you can see in this example, has 10s, 20s, 30s, 40s, about 50 in that case. And this was first found in the Back Rio Grande out in Portland. And nowadays, it's a very difficult site to get to. It's probably easier in those days, in the 1860s. But nowadays, it involves a long, long walk with donkeys, which apparently don't like carrying rocks up hills. And we end up with these very, very nice specimens, and that's a rather nice example. And so I will just point out some of the features on it and then some of the measurements that I make on these things to help us understand things. So first of all, let's change it to a diagram so we can actually see what's going on. Okay, so here's a diagram. So you have 2 teeth, an anterior tooth and a posterior tooth, which are AT and PT. And then you have the muscles. And I remember I talked about these muscle platforms, these myophores, and that's AM. And there's 2 of them. There's one which is a shelf, and there's one which is a projection down into the valve, and you can see that on the left. And then there's a posterior myophore that fits into a cavity. And then you have these 3 pillars, and these 3 pillars correspond to what we saw when we talked about the Hippurotids to begin with. And P0 is what we call a ligament. Well, what remains of the ligament, because there's no ligament really remaining there. That's just a ghost of where the ligament once was. And then you get these other 2 pillars, which are probably related to excretion of water from the Rudist. I've got a couple of other things. The E and the G in there. E is the zone which has been bored by organisms that lived on it once it died, and G is just a single large boring of a small boring bivalve that actually cut into the shell. But what I do is I measure a number of angles on these things, and I'm not going to go through them in any great detail. But these first 2, this angle here and this angle here, enable you to distinguish 2 types of these things, to which we use the term Barrettia, and the other one is Whitfield yellow. And we'll see some of these as we go further on. There's other angles you can measure in here. This is an important one because it tells you something about how the ligament is changing. Okay, so this angle here it starts off with a very long ligament and is a very narrow angle. And as you get on, it becomes progressively larger, that angle. And you can use that to the stage of evolution of these actual of these bivalves, these Barrettias. And so we can use that as a nice way of actually doing things. And then you can have some angles between the principal pillars, the P's, in this sort of thing. So that was the sort of background to what we do about these things. So let's just look at it. Well, if you just plot those first two angles up, it distinguishes your two different types of Rudists. So you've got Barrettias, which plot in one field, and your Whitfield yellows that plot in another. This is mostly data from the middle Campanian, above where we're talking about, but it's also got the lower Campanian ones put on here for reference, and they plot in exactly the same places. So this was conservative. It didn't change during the Santonian through to the middle Campanian. It stayed in the same way. And so they define two well-defined different genera at this point. Your number of rays, you can plot that up and you find that they're different as well. The only trouble is finding nice, big, complete specimens is not easy. Usually they're damaged, so you can't count the number of rays. So this is a more difficult way of actually looking at things, although it does seem to yield some results, but it's not so straightforward. The length of the ligament, which is one of the things I mentioned, that particular angle there, and this is two angles. This is one of the first angles, and the length of the ligament, which is the one on the actual y-axis there. And you can see that these two middle Campanian forms, the Barrettia monolithera and the Barrettia multilirata, both Jamaican forms, they plot right at the top, whereas this form around the Santonian Campanian boundary, this Barrettia russii, which is named after Russi's high school in Lucy, in Jamaica, it plots much lower down. And we'll find out that this is a very good way of distinguishing our Barrettias. Okay, so let me now go and give you a little brief tour of parts of Jamaica and some of these locations. So we have, that's my basic summary map of the geology of Jamaica. It needs updating, but it works for this. And we have these three areas in here. So we have, first of all, St. Anne's Great River Inlier at the top. Then we have the Lucy Inlier out in Hanover. And then we have the central inlier in central Jamaica, where we have the most or the largest number of sites. And this is all Santonian to early Campanian. So these are the oldest Rudists really in the Upper Cretaceous of Jamaica. So we start with St. Anne's Great River Inlier. I can go by that, I don't need that. Okay, so basic summary map showing some of the geology in there. I'm not going to go into any detail about the formations and things in there. This is published, it's free online if you want to look at it. But let's have a look at a little bit of the things. If you look at the sequence on the left, you can see it's thick. Okay, there's 1,000 meters in there of section. And there's a lot of gaps in the middle of it. There's a couple of faults. The upper fault probably cuts out maybe 3 kilometers of section. So there's probably a much thicker section in here. And the Campanian is relatively incomplete. Now, Ammonites are generally very rare in Jamaica, but you can actually see in here some Ammonites. And these are the same sorts of Ammonites that you would find in Texas. And so you can actually date these pretty well and place them into the Texas sequence. And you notice the second one up on the right is, and that's 5 millimeters across, that is our little crinoid Unticrinus socialis, which I said was really quite common. And the remarkable thing about Jamaica is it actually occurs to extremely great thickness, 250 meters. If you go to the thickest section elsewhere, which is actually the section I worked on in Yorkshire, it extends through 42 meters. So the sequence in Jamaica is much, much thicker than any of these sequences elsewhere. You also get the anisoramid bivalves, and these are anisoramid bivalves, and they always have this very typical sort of costate shape to them. And again, they're relatively used. And again, this follows pretty what is going to Texas, being exactly the same sort of thing. I had some others in here as well, but I haven't done that. And what I go on to do is to then show you some of the bivalves in there, the Rudists bivalves. And Rudists bivalves occur at several levels in there, but the Barrettias occur at 3 levels, well, there's a reworked one as a 4th level, but they occur at 3 main levels. So what we have is we have upper, middle and upper Campanian ones at the top, which we're not so interested in. But then we have this one, this what I've called Barrettia precoatsi, which occurs with the Untocrinus, and therefore it's clearly Santonian. It has to be Santonian. Okay, so that's what it looks like. It's not so easy to see the details of it. They don't photograph that well. Calcite on calcite, and it doesn't make life easy. If I annotate it, I can show you the features I saw before, but perhaps it's better just to actually look at a line drawing of it, and this is a line drawing of it. And you might remember that I said the length of the ligament was an important feature. So P0 there, you see that P0 sort of extends a long, long way forward and is actually very, very curved. Okay, and it arcs way around the 2 teeth, or the posterior tooth, which is shown in yellow. And this is effectively primitive. And look at the actual rays that extend in. They're pretty much straight. They're not made of beads like the one we saw before. So this is a very primitive Barrettia. In fact, it's the most primitive Barrettia we know of anywhere in the Americas. And since they don't occur anywhere else, it's the oldest one anyway. So that's it. It's just 2 specimens, okay, found in growing position together. I've never found another one. I must go back and have another look, but I've never found another one there. Not the easiest of walks to get to some of these areas. Let's go out west now and have a look at the Lucian layer. And the Lucian layer out in the west is situated here. This is my current map of it, and I published this in the paper recently that actually shows these Rudists. And there are 2 sites. There's one there at Maryland, labeled number 1, and there's one there at Clifton itself, which is labeled number 2, and it is down by Clifton Cave. And this is the Clifton limestone. This is the thin limestone that occurs within the sequence here. Well, I say thin. It's probably 40 meters thick, but then again, the actual sequence here is probably about 6 or 7 kilometers. So 40 meters is thin compared to a great thickness of sediments like that. Okay, so this is the type specimen. This is the specimen from Clifton itself, which is in the US National Museum, as you can see by the graffiti on it. I don't know why they can't put the graffiti on the side of it when they have to put it on the surface. It is worth illustrating. But and again, you can't see all the details, but we collected a lot of additional material from here. This is my best specimen, which is actually really rather nice and pretty. And you can see the very coarse cellular structure on the right-hand side, which is a blow-up of the left-hand side of the specimen on the left. And again, maybe it's, and the paper's there, that's free online as well. Maybe it's better to just look at the line drawing of it. And now you'll see that the P0 is shorter. It's not quite as long. It's dragged back a bit. And the rays in this case have poorly defined beads on them. And we use the term moniliform. Moniliform, yeah, moniliform, submoniliform for these. And it suggests it's much more advanced, or significantly more advanced than the one from St. Anne. There are other Rudists that occur in here as well. I mean, I mentioned Whitfieldiella, and this is Whitfieldiella, and you can see that the cellular structure is quite different in this. It's narrow, thin bands. But I'm not going to talk about Whitfieldiella much, because that would be a separate talk. So I'm just showing you that. And then there are some more classical, typical Hippuretids, a thing called Vasinites, which you can see the 3 rays heading into it. And these seem to be quite useful, but this is the only place in Jamaica that you actually find these. They're not rare, they're not rare there, but they occur across the Caribbean to Mexican region. So Curacao, Cuba, Puerto Rico, Jamaica, Mexico. We find them across this region. And they do seem to be useful. And I've measured lots of things on those, but I don't want to go into those in that much detail. So let's come to the central inlier, which has the more larger number of sites, shall we say. So if we come down in here, we can actually come down to the southwest part of the central inlier, and there are 3 sites in there, A and C. Well, A is the classic site, which was discovered by Tony Coates, hence the name of the fossil. C is one which was probably also discovered by Tony Coates, but nobody ever described anything from it. And we've collected that, and there's a lot of material there, which is interesting. And B was found earlier this year, and I'll show you some pictures from that. Okay, so let's have a look at them. So we'll start with Peters Hill, because that's the classic one. Okay, the stratigraphy, it's not so thick, a couple of hundred, 200-300 meters. And at the bottom is a Rudists-bearing limestone. And it doesn't yield that many Rudists. So here's Shakira sitting, well, standing by the Peters Hill limestone. The Rudists weather out, and you can find them. They're usually a bit eroded, but you can find them. Bioclastic limestone, fairly typical. We look at the rest of the sequence. It's got the ionoceramids as well. This is a little bit higher up, not so useful to tell us what it is. And then you go into a series of sandstones and shales. And there's even a limestone with cherts in there, black cherts, which occurs. But what we're interested in is just that Rudist, and this is a nice cluster of those Rudists, which we found there. It's actually upside down, so it had been turned over by a storm, and there's about 30 specimens in that cluster. This is the type material, which is in the museum here in Jamaica, in our museum in the department. And you can see some information there. Again, you can't see all the details. That's my best specimen at the top. Actually, it's not mine. It was Tony Coates probably collected that one, but I cut it up and found that it was rather nice. And then there's a detail there of showing the feature. You can see that we're back to these rather straight rays going into it, and the ligament, the P0, coming in from the top, is quite long. Okay, so again, the length of the P0 is quite an interesting feature and a useful feature to use in these Rudists. There's this other thing here, which also has 3 folds, a strange thing called Torreites, which doesn't have the, although it's a Hippuretiid or closely related to the Hippuretids, it doesn't have the nice sieving pattern on top. It was originally described from Cuba, but then was subsequently found in Arabia, in Oman. And Dietrich Saunders brought me a very nice specimen from Oman, which I have somewhere near me at the moment. So, anyway, I'll just show you this because it turns up again in a minute. So, all right, now we go and look at the new one. This is the new locality. This is at Main Ridge. And so this is situated in a place where we never ever had any old Rudists. And this was discovered earlier this year in March. And I've got all the details about this here. So I must thank the various people. So Philip, Paul, Akelia, and Hank, who were the ones that actually were on the trip that actually found this. And then the images of the actual fossils were sent around, and they were sent to me, at which point I said, wow, these are very interesting. And then we went down there with the team, which included Hank, and we collected this material. It's the usual situation with Rudists. Okay, they're big, they're heavy. We probably brought out about 200 to 300 pounds of rock, and it's always situated at the bottom of the hill. And you have to park at the top of the hill. And so what you have to do is to collect the things and then fill your rucksack up and then carry them up the hill. again, if I say, if you want to come collect Rudists with me, you're most welcome, but just remember you might have to carry a lot of rock. This is a nice little shot as we're moving down. We're about halfway down here and looking down towards the Rio Minho. The site is right at the bottom, so it gives you some idea of how far you've got to go down, which isn't the problem. It's the coming back up again. And then this is some of the rocks in the Rio Minho itself. So this is the main ridge formation, series of volcaniclastic andesites, stuff strewing off an active volcano at the time. Just not the sort of exposures you expect to find any fossils in. Okay, it's another view of these sort of things. You can see some crude bedding in there. And then, of course, the whole lot's been altered quite a lot. There's all these veins that go through it. So these are calcite, zeolite type veins. But on the path, just above the river, you find this. You find some volcaniclastics with some chunks of limestone. Okay, and when you start looking at it, you see it's a volcaniclastic matrix, but it's got these snails in it. Okay, fossil snails, fossil gastropods. These go by the beautiful name of Simplotixis nobilis, which has not really been described, but it's also present at Peters Hill. And then you get your Rudists. So here's some of the Rudists. Okay, there's a nice big cluster of Rudists. I must admit, all of these now back in our collections here, because you don't leave them there because these are quite rare. You don't find these things every day. Okay, and this is then, I've cleaned these up, and this is the left valve of them, the free valve. You don't see the sieve network because it's eroded away, but you do see the rays that are in there, and you can then cut them. This one's a bit recrystallized, but this one here on the left is actually nice because you can see the teeth and you can see the ligament, the P0, and you see it's got the same curved shape at the end as we saw in Brachiocoatzi, the actual tight material, and it's straight, and the rays are straight. So these are absolutely typical Brachiocoatzi. So this shows us that we've got the same age rocks in that part of Main Ridge as we had over in the other part of the Central Inlet. And I'll quickly take you down to Dry Hill. Oh, it should be Dry Hill, it's DR on it. So in Dry Hill, we have another set of Rudists, and this is what Dry Hill looks like. There's a cow in the middle there for scale. And you can see this is really quite a good limestone. Okay, a well-developed limestone, and the Rudists weather out of this. And these are the Barrettias. Again, you can measure angles and do all this sort of stuff, but if I give you a drawing, you can see here the P0 is shorter, and it's got back to the rays being more undulating as you go across them. The interesting thing here is there's loads of Whitfieldiellas, lots of different ones in here as well. And so this is one of them, which has rather crude rays. This is another one which has really rather narrow ones, which are rather well beaded. And this is another one which has these rather coarser rays with very large beads on them. So there's at least 3 species of the Whitfieldiella in there, which you can do the same thing as with the Barrettias, but we're really concentrating on the Barrettias today. And we also have our Toriites again in here, and these are rather nice specimens. The one on the left is one I got about 10, 15 years ago. And the other one is one which Roshan managed to find earlier this year, which is really nicely preserved in terms of the folds into the shell layer. Although it's incomplete, there's enough of it there to exactly tell us what it is. And you can see the three major folds on the middle specimen. And that's strange. The Dry Hill Rudists are strange in many ways because you have so many of these Hippuritids, and it's not very common in the New World. In the Americas, usually you only get 1 or 2, very rarely 3, extremely rarely 4. At Green Island, for instance, we have 4, but 5 is really only known from Dry Hill. So it's quite interesting of that, and they're probably different lineages, and it's just a coincidence that they're all in the same place. Okay, so let's now just try and pull some discussion out of this. Both Barretti and Whitfield show similar sorts of things, and they show similar sorts of changes. But let's concentrate on Barretti. So the ligament starts off long and curved and gets shorter. And that's probably the most useful thing to distinguish the age, in other words, date the rocks you're in. The rays change from these parallel-sided, these non-monoliform to submonoliform to actually monoliform rays. So you actually see this progressive change in the rays as you go up section. There's an increase in size, but that's not so useful. There are other things in ray partitions I haven't really talked about, and there's changes in the teeth, and I haven't really talked about that, but they can be found in the various papers I've produced. We go and we look at that angle of the ligaments, and this is plotting up a whole stack of different Barrettius from across the Americas. Okay, so this includes material from Jamaica, Puerto Rico, and from Cuba. And you can see this angle, this ligamental angle is on the right, and you can see it starts off very narrow and it gets progressively larger. And you can see the one from St. Anne is at the bottom, and then you've got our Barrettia coat size from the new site, and Rudists from Hanover sitting in the middle. And then you have all the other ones which are a bit younger, including the Irregularis from Dry Hill, which are sitting higher up, and then the middle Campanian ones above that. And so you can actually see there's a progressive change, and only one or two specimens will tell you about where you are in the stratigraphy. So it does make them valuable for stratigraphic use. But notice on the left-hand side, you've got this upper Santonian, you've got the lower Campanian, and I've got what I call transition in there because we don't know where the boundary is going to be at the present time. This is just showing you that of taking our 5 ones that we've sort of briefly talked about, and showing that they go from smaller ones to bigger ones, from left to right. The rays become more complex. They start off basically straight and they become moniliform as you go to the right, and the ligament gets drawn in. I'll just show that as I just go through these 5 shots of them. So you just watch the ligament and watch the nature of the rays. Okay, the ligament gets shorter. Okay, the rays are straight. Now the ligament is getting shorter again. The rays become beaded, poorly beaded, not very well defined. Again, ligament is shorter. Rays are poorly defined, beads. And then when you get up into the middle Campanian, you end up with a very short ligament and very, very clearly well-defined beads on the rays. So it does help you very quickly to work out whereabouts you are in the stratigraphy. This is my best guess at the moment for how you put those limestones in there. The limestone or the level in St. Anne Great River is clearly within the Santonian. There's no doubts about that. The central inlier site of which yields Barrettia Coatsai, both at Peters Hill and in Main Ridge, sits somewhere down there. Because the Clifton limestone has ones which are more beaded, I think it's a bit younger. And then, of course, the Barrettia Irregularis site at Dry Hill is probably younger still and probably sits up definitely in the Campanian. So it sort of gives us an idea there. There are some radiometric dates from Main Ridge, which are a bit younger than that. So that sort of seems to fit very well in with that. So what we're really saying is that Rudists, they're interested in their own right because of how they lived. And they're completely extinct. We can't go and look and see how they lived, but we can try and work these things out. But more than that, they can help us date the limestones that we have in the Caribbean. And we'll be able to date successions from Jamaica, compare them to Cuba, compare them to Puerto Rico, compare them to Mexico, and we'll get useful information. Showing you lots of these pictures is important because if you actually ever see any when you're out in the field, it's important that these are reported because we don't have as many sites as we'd like, and we'd like to get more. And the idea is to extend this, and I'm working with people in Mexico, in Cuba, it should be Puerto Rico, it says Cuba twice, and Puerto Rico on these things so that we can go forward. And for all their help, and I hope I don't miss that many people, I have to thank the various people who've lugged these damn big lumps of rock up hills, down rills, along rivers, or whatever it is. And you can see the series of names in there, and some of them are certainly listening to this. And without their help, it would be impossible to actually do this work because I cannot carry all of these rocks myself. It's impossible to do that. And I also have to say, and this is the Rudists display in the Smithsonian in Washington, there are vast numbers of people who have allowed me to look at their collections and have given me free access to the collections, and that is extremely important. So all of these people here are very important in terms of allowing access to these collections so that I can photograph these things and measure these things and go forward and publish many more papers on these Rudists. So with that, I will say thank you and turn it back over to Thera if I haven't used all the time up and there's possibilities for questions.
Thank you so much, Professor Mitchell. I really enjoyed the presentation. Harken back to a course called Z100, which was a survey course of both invertebrate and vertebrate zoology, where some of this structural features of the bivalves, the Rudists, was very applicable. And certainly also when we look at the corals and the crinoids, which I had a reacquaintance with last year when I was doing some biology tutoring.
All right, so wife, she will be home before me, so she should be there about 3:10.
Suknanan, are you trying to ask a question or make a comment?
All right. So you could put back some more bait hunting in the room, in that particular room. And
okay. All right. So thank you so much again. I am looking through, is there anyone who wants to ask a question or to make a comment on Professor Mitchell's presentation? Well, if there's no one yet, I'm going to ask Simon. So we know that these are fossils that you've been presenting today. Just out of curiosity, what are the closest bivalve molluscan relatives of Rudists that are extant today?
Well, that's a very interesting question. There aren't many things that are probably that close to them. There is a thing called karma, which is actually a tropical thing and which does occur around Jamaica, which people did at some point think were actually closely related, but they don't really believe there's a very close relationship anymore. The Rudists themselves probably developed from a group called the megalodonts, which are another group of bivalves, which actually also do occur in Jamaica, in the oldest Cretaceous rocks in Jamaica, in the area around Bembo. But those died out also about, well, in the lower Cretaceous, and those are about the last ones. And although those go back possibly as far as the Permian, although people say that maybe they aren't the same group in the Permian as the ones in the Jurassic and the Triassic, the Jurassic and the Cretaceous. But there really aren't any close ancestors. There's nothing. You've got to go back no, you don't really find that much that's close related to them.
All right. I'm gonna have another question if anybody else doesn't want to have the floor. The floor is open to anybody who's here, but I'll press on. So I know that you've actually examined some of the specimens that you presented today in other collections. About how many of or how well represented are the Rudists in, say, the collection that we have in the Department Geological Museum?
They're pretty well represented because I've collected vast numbers. And also people like Gavin Gunter, who did his PhD here, he collected a vast amount of material from Western Jamaica as well. So we actually do have some very good collections. It just needs more work to actually get them worked up and finished off. We're sort of going into a phase where we're trying to understand them in a new way and make the most out of them as possible. and that has really required the collection of very large numbers of specimens. But as you've seen, almost all of the specimens I showed, with the exception of the Puerto Rican material, are cut. So we also have to process them. So it requires cutting them. Now, that's not so bad if your thing is relatively small. It's extremely difficult if your thing is, 20 centimeters, 30 centimeters, 50 centimeters across. Cutting those sorts of things is not so straightforward. But we have a good collection. We have a good collection. I would say we probably have the best collection of Jamaican rudists in the world, without a doubt.
Okay.
We probably have every single specimen, every single species represented, maybe with one or two exceptions, which are only known from single specimens elsewhere.
Okay. Shakira Khan has a question. She had her hand up. Shakira, you can go ahead.
So following on that, just out of curiosity, how many new species are unique to Jamaica?
How many species? Well, Jamaica, in some ways, is quite interesting because when we look at the ages of the different parts of different limestones across the Caribbean and into Mexico, Jamaica has the Upper Maastrichtian, and most other places don't have the Upper Maastrichtian in the same detail as we have it, or in the same fascies which have the Rudists. So we have a vast number of additional species in that interval, which you don't see elsewhere. For instance, my recent, well, not recent, 10 years ago, I revised the Antilocaprinids, which big Titanocyclitis belongs to, and that sort of thing. We went from what was 3 genera to 10 genera. And I would say 6 of those are only known in Jamaica.
Quite impressive.
So there really is a very high diversity of things at that time in Jamaica. It would be elsewhere, and it probably is elsewhere. It just has not been looked at. I mean, you've got to remember that Barrettia itself was found in Jamaica in 1860s, and it wasn't discovered elsewhere. Probably until the early part of the 20th century. And now we know it from a large number of places. So we know it from Puerto Rico, we know it from Hispaniola, we know it from Cuba. It's obviously in Jamaica, we know it from Mexico, and we know it from California. So all of those places subsequently was founded, but it was first picked up in Jamaica and found in Jamaica. Equally, I mean, although Titanocyclitis is said to occur in many other places, in fact, most of the other things that have been called Titanocyclitis are a different one, which is something I've called Sarcolites, new Sarcolites. And the things in Texas are Sarcolites. A lot of the things in Cuba and in Mexico are Sarcolites, and it's mainly Jamaica that has Titanocyclitis, although there are rare examples of Sarcolites in Jamaica. So yeah, there's a lot. I reckon we probably, if you're talking about number of species that are only found in Jamaica, you might be talking about 50 or 60.
Impressive.
Okay, does anybody else have any questions or comments for Professor Mitchell?
Yes, this is Randy Parta.
Hello.
Yes, structural geologist, former student of Professor Michelle, Professor Robinson. Great talk. It's good to be invited to this talk, but I hope you forgive me because I'm not a paleontologist, but I'm just thinking about the importance of this. One, well, it's good that we categorize in the amount of Rudists for the Jamaica area, but the important for it in terms of the Caribbean region, in terms of the Caribbean evolution, because what it tells me is that in the Campanian time, Jamaica would have been an island arc, more or less. Well, described as
a series of bits of island arc in different places.
Yeah, series of bits. And St. Peter's Hill definitely has been quoted by Jim Pindell as one of these primitive island arcs. And it's interesting that you found that there. Also, and Jamaica would have been west of where it is using the Pindell model,
Yeah.
of
Yeah.
course. And
Yeah.
in front of it would have actually been the Caribbean plume, which is the large igneous plume being emitted. And you wouldn't expect that the root is there. But I guess the question and the comment is, this is very important from a Caribbean
I think one of the interesting things you can do is that these Rudists are relatively locally distributed. Now, what that actually enables you to actually do is to look at where they are found. And as we're getting more information and we're basically working out the different species that occur in the different islands and different parts of the islands, what we can actually do is to look at similarity matrices and actually look at how similar the faunas are in different places. And that will tell you how close some of these places were. So for instance, you have Puerto Rico, you have Cuba. They have a very, very similar fauna of Rudists. And you come to Jamaica and you go down to southern Mexico, they have a different one. And that's telling you where these places were situated at different times. And so
the evolution is different, right?
Yeah.
Puerto Rico is a different evolution relative to Jamaica.
Yeah, but what it tells you is how close these things were. These things could be distributed across those areas. So the currents must have carried them in those directions, but other places they weren't doing that. And so what you can actually start doing is saying, well, that looks more likely to have been associated with that. And it allows you another tool to say, well, these parts of the Caribbean must have been close together at that time, and they weren't necessarily at other times. So for instance, the Rudists in Toco bear much more similarities of those in actual Mexico and in Colombia than they actually do with the rest of the ones actually in Trinidad. And as you know, Toco area looks different. It doesn't fit with the Northern Range. And it would appear that that's actually quite a separate area that's come from a different part. And the Rudists will tell you where the affinity is with those sorts of things. So I think you can use them for reconstructing paleogeography.
I do agree with that.
Use that and that. And so I think that there is value in doing that, as well as in dating some of these things. They do give you good dates, particularly in some of these limestones where they don't work. Yep.
Yeah, and I found it quite interesting that you actually found similarities between the Jamaican Rudists and the Gulf of Mexico, which suggests one, the depth of the ocean at that time in the Gulf of Mexico area, and obviously our closeness to the Gulf of Mexico evolution, well, at least that part of the Caribbean. So I just think it's quite amazing. It ties in quite nicely with the Caribbean evolution, and it ties in quite nicely to the Toco area, which is Reef Point, more or less. I've been there. I've seen the Rudists there. It's quite intriguing, and I know it's good that this work is being done. It'll be very good if we could really categorize this within the entire Caribbean area, because I know in Tobago we have primitive island arc sequences also.
Yeah. I think this is the thing. I think as we go forward and as we get you've got to know what you're looking at. So you've got to look at the detail of what you're looking at, and then you can actually start adding the actual detail and doing this work, which allows you to actually put these things together. And because I've collected pretty much across much of the Caribbean, and if I haven't collected, other people have, and I've seen most of the material, I have a better feeling for what's across the whole of the Caribbean throughout the whole of the Cretaceous and how we can put that together. And I think this is a sort of tool that we can use as we go forward to try and explain where different parts of the Caribbean came from, and how then you can actually then start looking at the tectonics, you start looking at the igneous rocks and the geochemistry of those, and you pull all of this together to actually come up with a better framework, a more refined framework as you go forward.
All right, well, we've certainly begun to get a little bit heated and really into the interesting spin-offs from today's presentation. Simon.Mitchell@uemona.edu.jm if you need to follow up with Simon about anything coming out of today's presentation.
Or you can go on to sfmgeology.com, or you can go on to ResearchGate and find me on ResearchGate. Those are the easiest ways of done. ResearchGate is great because if you want a paper, I can send you a paper from that. And that's a very good way of getting hold of papers from people. So if people want any of these, some of them are freely online, But I think that that would actually be a good way of going forward. So for instance, the feeding, the paper with Gavin and Willem on the feeding of Titanocyclitis, that one is not freely available. So if people want that, all you need to do is to just send me things from ResearchGate and send me a request on ResearchGate, and I just send it to you.
All right, so thank you, Simon, for today's presentation. As you can see, the numbers grew. We had very good numbers today, certainly numbers greater than last week. And we've really begun to get into some very engaging discussion. Unfortunately, we are out of time for today's brown bag. And it is just for me to thank Simon for his presentation, which was very interesting and engaging, and to all the persons who signed in from wherever they may have signed in, whether in Jamaica or overseas. It was our pleasure to have hosted you this afternoon. And do look out for other flyers from us announcing other topics and presenters in the Brown Bag Seminar Series. So thank you all, and see you again another Thursday afternoon at 1 o'clock for some other interesting talk by another engaging presenter. Thank you, and thank you, Simon.
And yeah, thank you everybody for listening. And I hope you enjoyed it. That's all I can say.
Thank you very much. Have a good evening.